Hello everyone. In this video I'm going to guide you through the steps of creating a hardware platform that we can use for the Zybo z7-10 board, same as the ones that we used in the lab. So in order to do this, we need to use Vivado to create the hardware platform, and the first step that we are going to do is create a new project. Once we click here, you can also open it from File and New Project. We can create a new project. We have to give it a name. So in this case, I'm going to give it the name Hardware Demo. Click Next. Then it's going to be a typical RTL project, which is the most common project that we use here. Here we can add any design, any hardware design in VHDL or Verilog that we use. But in this case, we're not going to add any extra complexity. We are going to limit ourselves to interface with the peripherals that come already on the board. Here we can add constraints. Now the constraints are in any case that we want to interface with an external device, something that's not currently attached to the board but that could be attached to the board in a specific way. It could be a module that you can buy from Xilinx, or it could be some custom electronics that you have designed and that you want them to interface with your board. We will see how to create the constraints later in this video. Next, we're going to select the part number. In this case, we can select the part number directly from this list. However, if we want to, since we're using the board, not only the chip, and the board comes already with some peripherals installed, then we can select it from the boards tab to make our lives a little bit easier and we don't have to declare everything manually. We can click Next. Now we can see the project summary here, and now we can read some stuff. There are no source files, no constraints files, and everything seems to be right, so we can create our project. Once we are on project, we can see the project manager window. This is the main project window that we'll be working on. Here's the flow navigator. If you're familiar with any hardware kind of design flow, you'll see that these are all the process or all the steps of creating a hardware design. In this case, we are going to be using the IP integrator because we are going to use Xilinx IP in order to create our design. So we're going to create a block design, give it a suitable name as well. So same, hardware demo. So once we are in the block editor, we can add and remove blocks as we wish. So we can click on the plus sign here or here to add a new block. So the first block that we're going to add is the sync processing system. So in this case, the sync processing system is what gives us access to the processor and all the interfaces to the peripherals that we have on board. So we can double click here and we can see the configurations on it. We can see all the peripherals here. We can see the input-output multiplexer. We can see that there's a flash memory interface here. We can see some more ports. We can see the processors right there, the central interconnect, and the PL side of the board down here. So we're not going to be changing any of these configurations. Right now there's no configuration on it, but we will be using the defaults anyway. So now we have our processor. Let's add some interfaces. So the first thing that we want to do is that we want to add some interface to some of the peripherals. Let's say we want to interface with the LEDs. So for example, we want to interface with the LEDs. We need to create an AXI GPIO block, which is the block that allows us to interact with any GPIO port on the board. And in this case, we are going to connect the LEDs here. Now we could do this manually, but since we selected the board when we created the project, we have available this tab here that we can see our peripherals on the board here, and we can actually just take the LEDs and drag them onto the board, and you can see it will connect them immediately or connect directly. And the same we can do with the RGB LEDs. We can connect the RGB LEDs, and we don't have to stop here. We can add as many as we want or as many as the board will allow us. So we can connect a couple more. So in this case, I'm going to use this one to connect the buttons and the switches. going to be connected to this block. Now, one important thing about adding these blocks is that we can give them names. So every time we add them, Vivado gives them an automatic name here to each block. However, these blocks are not very descriptive. So when we click on the block, we can come here on the block properties and we can give them names. So I'm going to say that this block is called LEDs, and I'm going to say that this block is actually called inputs. Okay. Let's get rid of the sound. That's a little bit annoying. So now we have our LEDs, our inputs, but these are onboard devices. What if we wanted to add some devices that are not connected to the board? What if we wanted to connect a screen, or in this case a 7-segment display or a keypad? Let's add another block. So ICGPIO, one more time. We're going to connect this one. We're going to put it on top here. Oh, let's move it on top. I'm going to call this one SSD, and I'm going to double click on it to give it a custom configuration. And this configuration, in this case, because it's a 7-segment display, the type of 7-segment display that we're going to be using in the board, it's all outputs, and it has a width of 8 bits. So you can see it automatically selects some options for me here. It says the default output value. So we can click OK. That will be configured. And now let's do the same for GPIO. This time I'm going to put this one on the bottom here. This one is going to be the keypad. So I'm going to do the same thing. Give it a name. I'm going to go inside the configurations. I'm going to say that the configuration is custom. It's not, so a keypad, if you ever interface with a matrix keypad, you'll know that the bus width, in this case, it's usually interfacing. It's just a hexadecimal keypad. It has 8 bits, and 4 of them are inputs and 4 of them are outputs. So in this case, we cannot select all inputs or all outputs. We have to leave it both unchecked. But I want to show you what happens if I click on all inputs. Look at what happens in the options here when I click all inputs. See, both of them are blocked now. And we can see in the information here, it says Bitstream format supported, and it's just some help on how we can express this thing, but we cannot change these numbers anymore. If we select all outputs, you can see that the default tri-state value is the one that gets locked. However, the default output changes, but we don't want that. We want inputs and outputs, so they're both editable. Now, we don't want to change anything here. We don't want to enable dual channel because we want this block to control only one device. So in this case, we'll leave it as that. And now we have declared all of our blocks. So this now takes care of all the peripherals that we want to interact with. So now we can go here on the screen bar and run this automation. So this will take care of doing the connections automatically between the blocks as good or as best. The Vivado will try to do the best it can to connect all the blocks together. So we can select all the blocks here. We can click OK. And now you can see, let's optimize the routing. So this looks a little bit better. Let's organize this thing a little bit like that. If we zoom in, you can see that our keypad, as you can see, look, the keypad got connected to buttons, and the SSD got also connected to buttons, but we didn't want that, right? So let's go back and double click here. Let's change this back to custom. The IP configuration, we'll have to do this once again. So this is the keypad. So we're just going to leave it like that. And I'm going to change this tag also to be keypad. So that way it's easier to recognize. Same thing we're going to do here. We're going to go custom. In this case, it's all outputs because it's our 7-segment display. And I'm going to go here SSD. That should be fine. All right, so now we can run, we can save this. Everything is connected, everything is good and well. So now the next step, once we have done all the connections, is that we can go here. Well, let's connect, run the block automation. The block automation will do some configurations of the processing system. As I said before, we're going to use the default, so we don't need to change anything. So this will change the configurations of the processing system. So let's wait for it to finish and I'll show you what happened here. So remember that when we double clicked on the processing system at the beginning of the video, there was no configuration on it. There were no peripherals or anything declared or configured. So now if we go now again, we can see that we have some stuff. So we have some UART connections, we got GPIO, we got SD, we got USB, we got Ethernet, and we got some more configurations that we cannot see here, but if we click on this column here or if we click around on these blocks, then we'll see that there's some configuration that took place when we did the connection automation. So now that we have declared or we have our block design pretty much finished, we have all the peripherals right here that we want to interact with. All we have to do is go to our sources tab, right click on it, and we're going to create an HDL wrapper. Now an HDL wrapper is basically taking this block design and turning it into a PHDL file. So as I've said many times in this video, you can just let Vivado manage this automatically. We're probably going to see some warnings pop up here, but there's no problem. That's kind of expected. Warnings are fine, errors are bad. However, these warnings, we don't need to worry about them. Once this updates here, you'll see that now this is the design, the block design is replaced by a demo wrapper, which is a VHDL file. And if you're familiar with any VHDL, you will know how to make your way on this video. So first we have our entity declaration, which is a bunch of basically the top level entity or the top level of our design, which is basically as if we had wrapped everything into just one block with inputs and outputs. So we have there all the inputs and outputs that we've declared, and down here we just have a bunch of blocks that are connected together. This type of architecture, of this type of syntax, if you know VHDL, then you'll see, or you can recognize immediately that this is a structural architecture, and this is what we see here. So the only important part of the wrapper that we want to focus on is any device that we have declared manually, that we didn't declare from the board definition or from a library that we might have imported. In this case, there are two devices that we included, namely the SSD and the keypad, that we just we added them, we brought them into our design without any configuration. We just said it's 8 bits, it's outputs, it's input outputs, and that's it. But how do we tell really to the project where are those outputs, where are they connected physically? Because we have declared them in the design itself. We have to find a way, or we have to tell Vivado where to route those ports. So in this case, the place to look is in the entity declaration for our design, and we can go here in the bottom, and at the bottom we'll see all the devices that we have. So you can see the buttons here are already that we have already taken from the board definition. These are fine. The ones that we want to focus in is the keypad and the 7-segment display, because these ones are the ones that we have to declare manually. The project doesn't know where we are going. The project knows where the buttons are located because that's part of the board definition, but it doesn't know where we want to connect our keypad. So this is where we go, and we're going to add a constraint file. So we're going to create a constraint file. Create demo constraint. And inside this constraint file, it's empty now. I'm going to go and copy and paste the master constraint file. Master constraint file is basically a commented file that has all the ports that are available on the board and that we can access to. So in this case, we are going to connect the SSD between the headers, the PMOD headers C and D, JC and JD. So what we're going to go in this case, again, if you're familiar with Vivado hardware development, you will know this, you'll recognize this. If not, then not so much. Okay, so I'm going to use the 4 first pins of this PMOD file or PMOD port, and the same as these ones, and I'm going to basically copy the name that I got from my wrapper. So in this case, I'm going to start with the 7-segment display. So the 7-segment display, as you can see, by the way, you can see that the 7-segment display I declared as SSD. However, Vivado added this name. So this name here means tri-state buffer, and O means output. So this is an SSD output, and it's a logic vector of 7 down to 0, which means 8-bit wide. And the keypad, you can see it's also a tri-state buffer, but it's I/O, so it's an input-output buffer, also declared as an input-output, and it has a width of 8 bits. So let's go back to our constraint file, and let's change these names here for the declaration of our 7-segment display. So in this case, let's go there, 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 and there. Now notice that this is 0. It should be 0 to 7, and here we got 0 to 3, 0 to 3, so we need to change this to 4, 5, 6, and 7. Now, this, as I say, when you're connecting these devices, you have to know very detailed, in a very detailed manner, the inputs or the pins, the pin ordering or the pin arrangement of your design. This is something that as hardware developer you need to know, and there's no other way to do it. You need to know the hardware mapping of the pins in order to do an effective connection, because this is going to be routing those outputs or input outputs in this case to the appropriate places. So let's go back to the wrapper. This time I'm going to copy the keypad, and I'm going to place this here. Just replace this name of the port for that. Okay, so now we have declared the devices, the SSD and the keypad manually, and we are basically done. Now that we have our hardware design, we have our constraints, we can go straight down to here and generate Bitstream. So we can generate it, and this is usually a computationally intensive process, so it's going to take a while. So I'm just going to wait for a couple minutes while it finishes. Alright, so the Bitstream has been successfully generated, so we can go back to the next step. So once we generate our Bitstream, we can see it's generated here. The first thing we need to do is to export the hardware. So we need to take this Bitstream that were generated alongside with the configuration of the board and export it so that we can create a software project on top of it. This is a very easy step to do it. It just takes a second, and once we're done with that, we can launch the SDK. Launching the SDK, if you're not familiar with it, SDK is a software development kit, and this is the Xilinx software development kit. So that means that with the SDK or within the SDK, we can develop our software application. Once it loads, we need to let it finish initializing all its process. If we were trying to create an application right now when it hasn't finalized, then we could get into troubles because we could create a problem with the configuration. So we just need to be patient and let it finish do its thing. All right, once the SDK have started completely, we can see that we have the hardware demo wrapper here. So this means that we can have the specification of our hardware design right here. We can see all the address map, device information, IP blocks present on our design, and with this we can start our software project. So we can come here, click here and create a new application. I'm going to call it demo. Now the next step is when we create a new application project is to give it a OS platform. So in this case it can be standalone, Linux, or FreeRTOS. In this course we'll be using FreeRTOS, so that's what we're going to choose. And usually I like to start with a clean, fresh, empty application. So in this case, let's do that. As I said before, just let it finish. We can see the progress bar down here. It's very small, but it works. And once it's done, you can see that your project appears here on the side, and it has the SRC or source folder where we're going to have all of our source code. So let's create a new source file. In this case, I'm going to call it main.c. This is the file where I'm going to save all the information, and I already have a file prepared here. So I'm going to select everything from this file. And we're going to paste all that information in there. Now you can see that in this case I have a warning here that is saying this pmod keypad file is not there. So let's add this file because it's not in the project. So I actually have it. It's here. So these two files, I can copy them just like I would do regularly, and I can paste them here. So now I have my files, and I can go back to the main file. So here, the first thing that we need to do is, in order to import our devices, in order to import the peripherals, we need to find where they are in the configuration folders. So the main configuration library that we're going to be using is the xparameters.h, and the SDK offers us this nice shortcut where we can press Control key, and you can see that I get this little hand icon or hand pointer cursor, I don't know, and we can just click on it, and this will open up the parameters.h file. So in this case we can go there, and I have some declarations here for some macros, but they are empty. As you can see, for example, SSD device ID. This is the device ID or the ID number that Vivado has assigned to our project. So we can go here, and in this folder or in this file there's a lot of definitions. There's a lot of stuff that we can look at, but we are looking for something very specific. We are looking for the definitions of GPIO devices. So let's see if we can find them. We can see definition of peripheral processing system, peripheral processing system. Let's keep going. Definitions for driver GPIO, and there's 4 of them. So this is the place where we want to be. So in this case, let's look for the names. We have keypad, inputs, LEDs, and SSD. So let's look at what the first one is SSD. So I'm going to go device ID of the SSD, and I'm going to copy that macro, paste it in here, and I'm going to do the same now for the keypad, which it's right here. So I'm going to copy the device ID, paste it in here. Now the keypad also needs, or in order to work with the keypad, we actually need the base address of it. Base address we can also find in the definition of the keypad. So you can see here we are, and this is high address and base address. So we're going to use the base address. Then RGB and LEDs are both under the LEDs device here. So I'm just going to copy this one twice. Now this is important. We can actually copy the value of it instead of the macro. However, if for some reason the hardware platform should change and the device ID changes, then we are in trouble. So it's always a better practice to just copy the macro in this case. And for inputs, switches and buttons are the same. So switches and buttons can have the same macro definitions. We can save this. And if we have done all this correctly and our file is written, or well, when the file shouldn't be written there, but this is just a test project, so we can try it. The next thing, once we have defined the IDs of our devices, is to define the channels. So the channels come from the block diagram, and we can see in the block diagram that every AXI GPIO block has 2 channels, but not necessarily are being used. So for example, the LEDs block, it's using the 2 channels, one for the 4-bit LEDs, one for the RGB. The input block, it's using one for the buttons, one for the switches, and the SSD and the keypad are only using 1 channel. So in this case, with that information, we can go there and give it the appropriate names. For example, the LEDs, channel 1 is the 4-bit or the green LEDs, channel 2 is the RGB LEDs. So if we go to the software here, we can see the RGB is channel 2, green LEDs is channel 1, SSD and keypad are only 1 channel only, and buttons are channel 1 and switches are channel 2. So let's see here, inputs, buttons are channel 1 and inputs or switches are channel 2. So with that, we have all the definitions that we need in order to start our project. So now we can start declaring devices, initializing them, and interacting with them. We will go into that part later. However, I want to show you this running. So the next step in order to run, because I have the file and the project set up with the solution files. So the first thing I want to do, or before I run the project, is I want to connect to my board. So the first thing, I'm going to turn it on, because right now it's off. And I'm going to connect to it by clicking here on the SDK terminal. Port number, in this case, in this computer, is COM4. Remember, never connect to COM1, as COM1 is an internal port for the board, or for the computer. COM4, in this case, it's the one assigned to the terminal. You can see this connection status here is connected. And now the next step before running the project is that we need to go here and configure or do the configuration for our project. So configuration for our project goes here. We double click on System Debugger, so that brings up this window here. We must check all of these boxes, and you can read the description of what this does here. Basically resets the FPGA, it programs the PL side of the FPGA, it runs the initialization file, and then it runs the configurations. So if we've done everything correctly, this should be pre-populated for us. The processor has been selected, the linker file, it's already selected. So if everything looks good, and it does, we can click apply and run. Here in the SDK log, we can see the processes that are taking place. And once it's finished, it will start running the project on our board. So we can see here, app ready, input commands through the keypad, and execute with button 0. So I can actually press, I'm not looking at anything, but you can actually press, and if I press thing, command 88 is not implemented. Let's actually do one that is actually working. So RGB change, let's do another one. So in this case, this is changing the color. So we can change the colors here. And once we're done, we are finished. So that's how you completely create a hardware platform from scratch that uses the peripheral devices and manually declare devices as well on the Zybo Z7-10 board.